Hi guys, let me get my face out of the way of this. Okay. Now today, this lecture takes over from the tables lecture and discusses how to implement, or at least how hash tables work. Okay, so I discussed earlier, hash tables are a way of handling sparse table data by not having to store every part of the data. Now, what a hash table implements, as I discussed earlier, is a map. So I'll start by going over maps, and I'm going to use the book for a change, because I think by now everyone's got the book, and if you don't, tough. Okay, now, a map is got values and keys. Okay, otherwise known as associative arrays. So, we see some examples of maps. You take a student ID that goes to the student record, your N numbers in our school get turned, and if you type in your N number, we can get your transcript. Host names such as this can turn into IP addresses. So every time we go to something like this host, bookshelf.vitalsource.com, gets turned into some sort of IP address. That is what the system really thinks of, but is not really human readable. Since if you read 208.215.179 or 146, and there are all sorts of, every login system basically is based on maps, and just about every, it's just tremendously, it shows up everywhere. And your project is on a map of the transactions occurring in a system. So we'll talk, blockchain is based on maps. All sorts of stuff is based on maps. Okay. So what is the map ADT? We discussed that a little bit last class, but we talk about these are the important parts of the map ADT. They get the size. Is it empty? Get the value with a K, put KV, and so now the map in Java util is what you'll be implementing for your project, and here is this quick discussion of what happens. It's using integer as the thing, so it's a map of numbers and letters. And there we see the interface. The map is an interface, and we see all the normal stuff in the map. The actual map interface, which you've seen, has a few other things in it, but basically what we have here is size is empty, those are all clear. Get K key, so that's going to get the value from the key. This will put a key and a value, and it returns the actual value you're putting in. Remove a key, also returns the value of the key you're removing. Get all the keys, get all the values, get all the pairs. That's what's going on with this interface. And so I gave you a stub that has all of the important stuff in it for your project. And here we see some example. I'm going to skip by all of this stuff and get to hash tables now. So this can be useful. This one goes through and shows you some fragments that might be useful for your project. You probably want to read this stuff on page 409 to help inspire you for writing the project. Your project is going to be a little different, but because you're not making integers, you're using a linked list. Not using, an array, it's a linked list and all that, but it gives you an idea. And what I want to get to is hash tables, because hash tables are a way of implementing. This is the standard way. That's why when the thing came up, it had a hash map in it, which is implementing the map as a hash table. Now, the idea is if we implemented it as an array, using, say, if the keys were integers or something. We could have an array of, let's say, if the keys were letters, bytes, then it'd be easy, because we just need an array of 256. That wouldn't be any problem. But if the arrays are if the keys are things like strings, like people's names or websites or something like that, that won't work too well. Now, what we really need is we need to be able to store without building a table to fit every last key. So what we're going to do is instead put sometimes multiple keys in the same location. Multiple key value pairs in the same location. So and the locations are going to be an array, and what we're going to use is something called a hash function. That's going to map our keys into integers in a table. The only problem with the hash function is sometimes since we can't make each key have a unique hash, sometimes two keys will hash to the same location in our hash table. And that's how we get hashes in hash tables. Now, so if each key generated a unique location, that would make our life easy. We could just build an array, but once again, we want the locations to fit into our array. Now, so if our array is of size n, we want our location to fit into the array. Now there's various ways to do it, but the standard way to do it is just use mod n, the percent sign. So what I'm going to talk about now, let's go here. So talk about hash tables. So function maps key from a map to an integer location hash array. Okay, so here we have a key from a map. It's got to be mapped into an integer location. Now, to work well, all locations must be possible. So, hash of x equals the 0 function does the hash, but is not a useful hash function. Right, so if we map everything into location 0, essentially we are creating a list instead of a hash table. And also, to work really well, the locations should be equally probable. Okay, we might discuss a little more on that, but basically all hash locations. And So what we use, so first translate to integer, and then n is the size of the table. So that's what hashing does. And so we translate to integer, and then we take mod n to fit it into our hash table. Now, the problem is collisions when two key value pairs land on the same table location. Okay? If some locations were more probable, then they would have more collisions. So, in the worst case, hash of x equals 0 makes everything collide. As soon as you have two guys, they're going to land on 0. But even if 80% of the time it was in 0, that would make 80% of the time you have a collision. The lowest collisions are when everything is equal. So, what we want to do, what happens when there's a collision? Well, let's go back to the textbook. Hopefully, actually, I'm not sure I read that part in the textbook. So, new textbook for me. Okay. So there they're talking about different ways of hash coding. I'm going to jump over that for a second. And here we talk about collisions. Okay. So they're trying to minimize the collisions for English words. Okay, they're talking about hash coding in Java. Yeah. Okay, so okay, now, what do we do when two things crash into each other? They're still talking about hash functions here. Collision handling schemes, that's what I want to get to. Okay, now, so the idea is to have something like this. And let's call each of these guys a linked list. Okay, I'm going to go back to that. So if each of these guys is a linked list, you have an array of linked lists. And they're going to talk about what happens when that's a problem. But I don't want to get into that now. I'm going to talk about, just want to talk about this case where so you have an array not of values, but of a linked list of values and keys, value pairs. And that is the normal way we implement a hash map. So, here's a hash map. An array of not the key, of linked lists of key value pairs. And so, if you look at the hash table section of the book, you're going to see that they go into a lot more detail than I want to lecture you on. But I'm hitting the high points here. Now, there are cases where you don't want to use linked lists, but they're rare. They have to do with real-time programming, special purpose machines, extremely large data sets, and so on. For most non-exotic things, this is the way it's done. And so, and that is where I want to stop. Next lecture will involve average, worst, best case times. I think it's fairly clear that the hash map, the best case, is when it's the first item in that linked list. It's the time it takes you to compute the hash plus searching the linked list, which is best case is O of 1. It's very much like the linked list, except it has to do with, except instead of one linked list, we're averaging over all the linked lists in the hash map. And we'll talk more about that next class. So I'm going to stop here.